he and I are having a conversation, and he's like, it's time to go stream. Going to need isn't? It's clearly not. Those are just CSVs. Find the plot. Name of the silly plot. I can go and look up. So I had all this stuff like planned out and set up yesterday, and then my computer decided it wanted to run an update and restart itself. So. other idea.
This. I'm gonna find this. Now I'm being stubborn. I don't know if it's this one or what is the name of those bloody plots? I cannot find this. What the heck? I am so mad that it just lost my spot for me. No, and no. Not you at all. It's a nice SAT word, and we can pull back on that. But this was my plan for the stream, and I can't find it. Oh my goodness. I will continue looking around like a silly person. No, it's not that. Let's see. Heat maps, no. No, it's not this. It's not this at all. I cannot believe I can't find the stupid thing. The name of these plots. I can see in my head what the plots look like, and I cannot remember the bloody name of them. Oh, here we go. Here we go. I think it's this. I think it's this. I think it's this.
We are one step closer.
So. Oh, wait. Good. Now we want this one. Might have maybe. This one. Come on. Oh yeah, this is it. Oh yeah. Okay. So rinse. Okay. Why don't we just download this? Why don't we download this and then print it? Okay, there we go. Print. Oh my god, we're almost there. Oh, we almost there. Oh my. Oh. Okay. Let me set up my OBS now. Let's see, it's this. That's really big. Okay. Smaller because right now it is larger than the literal screen. No, it's up right there. Do that. Okay. Make sure it's on the right spot. Oh, I see. That's what it was doing. Okay. Excellent. This. Oh, that's wonderful. That's wonderful. This. Beautiful. This. There we go. There we go. Well, that was a journey. So, today we are taking a diversion and we're diverting over to this. I'm going to try and do this without my tablet because that's going to make everything a little bit of a pain to do. But this is something that came up in my research. And so I am taking the opportunity of this stream today to go through the paper because I actually need it. So I was like, aha, I can steal the opportunity that I already have. That's what we're gonna do, Should this be a Sunday morning paper? Possibly, but I want to try and get through this. So, now 26 minutes into the bloody stream. Whew. 26 minutes into the stream. We're actually going to try. So, we are looking at something called a Taylor diagram after Carl E. Taylor. And summarizing multiple aspects of model performance in a single diagram. This is very important. You have a model that's supposed to predict or describe or explain in some way some aspect of some physical state or physical process. As the saying goes, all models are wrong, some models are useful, right? So it's gonna be wrong in some sense. There's gonna be error built into the model. It just is. You're always gonna be taking some sort of shortcut in your model, either because sometimes it's because there's no closed form solution to the mathematics, right? The only solutions are, function approximations, and so you end up with this, say, like a Taylor series expansion, right? So you have this functional expansion of the result, and that's the only way that you can get any sort of result. But that theoretically goes on forever, so you're cutting off at some point because you can't have a model that goes on forever, right? It needs to be useful for something. So you're building an error there. Or you're applying the model through a computer, right? And a computer has rounding error in it. Because computers are not, they're very precise, but they're not infinitely precise. And that sort of rounding error can build up if you're doing a lot of computation. These sorts of things, right? So you're going to have error in your model, whatever it is, right? Or you could say, I know for a fact that I am missing some aspects of the physics that's going on. I know I don't know everything, right? I don't know what I don't know, but I know that I don't know everything. But I'm going to take what I do know and look at the error between what I do know and what I don't know, and that'll kind of bound the how much I know and how much I don't know, right? This starts giving me a way to look into the things that I don't know. So anyway. So the usual initial step in validating models of natural phenomena is to determine whether their behavior resembles the observed. Yep. You have a model that says the weather is going to do X. So then you go and look at the weather and ask, did it do X? All right. Typically, plots showing some pattern of observed variation is reasonably well reproduced in the model are presented as evidence of fidelity, right? So yes, it did indeed do X. For models with a multitude of variables and multiple dimensions, for example, coupled atmosphere ocean climate models, visual comparison of the simulated and observed fields becomes impractical because you could be talking about 15 different variables that you're taking into account, right? So if you were trying to plot this, you'd have a 15-dimensional plot, and you can't. It's not very useful. Even if only a small fraction model output is considered. It is then necessary either to focus on some limited aspect of the physical system being described, for example, a single field such as surface air temperature, or reduced domains such as zonally averaged annual mean distribution. So in other words, I have to restrict down what I'm looking at so that I can communicate what the model's doing, right? And so maybe I can't look at the whole thing that it's approximating. Maybe I have to look at one output, right? This is the temperature output, or I'm only looking at this small area of the globe or something like that, right? Or to use statistical summaries to quantify the overall correspondence between the model and observed behavior. So then I'd say, well, I can look at, so I have a model that's going to estimate the temperature at ground level across the entire United States, right? And then what I do is I want to validate to see how effective that model is. I get data from all the ground stations that take temperature. I compile all that data, and then I compare that with what the model said the ground temperature should be in that spot. And I take all of that as like some error, right? So I might have a median absolute error and then some error bars, right? So that my standard deviation or the median equivalent of standard deviation, something like that, right? In this paper, a new diagram is described that can concisely summarize the degree of correspondence between simulated and observed fields. On this diagram, the correlation coefficient and the root mean squared difference between the two fields, along with the ratio of the standard deviation of the two patterns, are indicated by a single point on a two-dimensional plot. So what are we looking at? We are looking at correlation coefficient. That's number one. So that's the correlation coefficient is saying as I vary, like as variable one goes up, does variable one go up as well? Does it go up less but still go up? Is it inverted? Does it go down like that? Right? All these are different, you know, is there a relationship, a linear or nonlinear relationship between the variable I'm looking at and another variable, right? That's what I want to know. Are they correlated in some way? And the root mean squared difference, which is exactly what it sounds like. It is the square root of the mean squared of A minus B. That's the root mean squared. It's literally that, right? So what am I doing? Why am I doing it this way? Well, I'm getting the difference between them, right? I'm getting the average difference between A and B, but that could be negative, so I want to account for the negative. So to get rid of the negative, I'm squaring and taking the square root. That's all it's doing, right? So anyway, along with the ratio of the standard deviation of the two patterns, right? So how much, so, say I'm plotting a bunch of, I have all this data, right? And that's A is this data and B, can you see it? You can't really see that. Okay. Let me try that again in a way that you can see it. Race. Okay. A's data is say like this, right? Blah, 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 bunch of things. B's data is like this, whatever, right? And I've got some mean and standard deviation, right? If I were to plot these all out, there'd be some mean and some standard deviation. This is a standard curve, right? And I'm looking at the mean and standard deviation of B, right? So there's a standard deviation. And anyway, I'm looking at the ratio between these two, the standard deviations of these, because if one is really spread out and one is very narrow, right, the standard deviations are going to be different. So that gives me, by looking at that ratio, I can tell, is one much more spread out than the other, right? Because if, let's say, A has a mean of 5 and a standard deviation of 2, right? And B has a mean of 10 and a standard deviation of 1. That means this is a much narrower peak, right, than this is. The standard deviation is half. So if I took the standard deviation of A over B, right, that would be 2 over 1. So now I can say 2 is twice as wide as 1 is, right? It gives me kind of an understanding of how spread out the data is between the two, right, as a comparison between the two, which is ultimately what I'm trying to do. Because one of these is the quote data unquote that's put out by the model, and the other is the data that's actually collected. Okay. Together, these statistics provide a quick summary of the degree of pattern correspondence, allowing one to gauge how accurately the model simulates a natural system. The diagram is particularly useful in assessing the relative merits of competing models and monitoring the overall performance as the model evolves. Because since you're taking all of this data, right, and condensing it into a single point, you have a single point on a 2D plot. Now you can evolve that over time and watch as that point turns into a curve. The primary aim of this paper is to describe the new method for diagram, figure 2, and to illustrate its use in evaluating and monitoring climate model performance. Methods for indicating statistical significance of apparent differences, observational uncertainty, and the fundamental limits to agreement resulting from unforced internal variability are suggested in Section 4. Section 5, the basis for finding appropriate, quote, skill scores is assessed. Finally, Section 6 provides a summary and a brief discussion of further potential applications. All right. Theoretical basis for the diagram. All right. The statistic most often used to quantify a pattern similarity is the correlation coefficient. The term, quote, pattern is used here in its generic sense, not restricted to spatial dimensions, and consider two variables, f of n and r of n, or I'm sorry, f sub n and r sub n, right? So it's n individual measurements of f and r, which are defined at n discrete points in time or space. The correlation coefficient r between f and r is defined as follows, right? So this is how you define the correlation coefficient. So 1 over n, you have a normalization constant here. The difference between my nth point and the mean of f, the difference between the nth point in r and the mean in r, summed up over all of n, divided by the standard deviation of the two. We've seen this before in covariance matrices, right? This is a covariance measurement. Where f and r, in fact, this is correlation coefficient is a normalized covariance matrix. So if you just took this top part, you didn't divide by the standard deviations, this is your covariance between the two. And when you divide by the sigma f, sigma r, it becomes a correlation coefficient. Okay. Where f bar and r bar are the mean values, sigma f and sigma r are the standard deviations of f and r, right? For grid cells of unequal area, one would normally be modified in order to weight the summaries by grid cell area, right? So if n is not evenly sampled, then that's going to throw all of this stuff off, so you have to account for that. The same weighting factors would be used in calculating sigma f and sigma r. Similarly, weighting factors would be used in for pressure thickness and time interval can be applied when appropriate, right? So in other words, if again you're counting it over any variables space, right? It could be literal physical space, it could be time, it could be my pressure gradient, it could be my temperature gradient, it could be any of a half dozen different things. Yeah, so blarg, right? So that's it. You have to take those things into account if they're unevenly spaced. That's all. The correlation coefficient reaches maximum value of 1 when for all n, the difference between fn and the mean is just a scaled version of the difference between Rn and mean. In other words, they are varying in the same way at the same time, right? If they're doing this, they're parallel to each other, then your correlation coefficient is 1. That's maximum. Where alpha is a positive constant. In this case, the two fields have the same centered pattern of variation, but are not identical unless alpha equals 1. Thus, from the correlation coefficient alone, it is not possible to determine whether two patterns have the same amplitude of variation, right? They're just varying in the same way. That's the only thing the correlation coefficient is giving you. a statistic most often used to quantify the differences between two fields is the RMS difference E, so root mean square difference E, which for fields F and R is defined as 1 over n times sum F and R n's, right? So it's the difference at point n between F and R. So that is like if I take the slice at this point n, what is the difference between this and this, right? And then I sum those over all n, right? And then I divide by 1 over n to normalize it. Take the square root. Easy peasy. Take the square root because I've squared it. That's all. Okay. Easy peasy, lemmy squeezy. Okay. The geometric relationship between the correlation coefficient R and the center pattern. Okay, that's once I start plotting. Anyway. Again, the formula can be generalized for cases when grid cells should be weighted unequally, right? There's just, you have to count some, if you have bigger squares and smaller squares, you have to count the bigger squares more. In order to isolate the differences in the patterns from the difference in the means between the two fields, E can be resolved into two components. The overall bias is defined as E bar is F bar minus R bar, right? So it's the mean of one minus mean the other. That tells you how much it's moved up and down. And the pattern and the centered pattern root mean square difference is defined by this. So what we've done is we have subtracted, we've just put this into here, right? So we've just, yeah, this is just a literal root mean squared, right? But it's the difference between F and the mean and R and the mean, and then we square root. All right. Okie dokie. The two components add equilaterally to yield the full mean square difference. E squared equals E bar squared plus E prime squared. Did we define E prime squared? I don't think we have. Oh, E prime squared is that correlation coefficients R, center pattern RMS. Okay, so they just geometrized it. Sure. The pattern RMS difference approaches 0 as the two patterns become more alike. But for a given value E prime, it is impossible to determine how much of the error is due to the difference in structure and phase, and how much is simply due to a difference in amplitude of the variations. The correlation coefficient and the RMS difference provide complementary statistical information, quantifying the correspondence between two patterns, but for more complete characterization of the fields of variance, or standard deviations of the fields, must also be given. All four of the above statistics, R, E prime, sigma F, and sigma R, are useful in comparisons of patterns, and it's possible to display all of them on a single, easily interpreted diagram. The key to constructing such a diagram is to recognize the relationship between four statistical quantities of interest here. We have echo. We have echo. Echo, echo. We should not have echo. Let's see. That is off. Hold on one second. That's off. That's off. That's off. That's off. Test. That's not gonna. Sorry. That's not gonna. Test. 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 No, I heard that echo. Is it still there? Do you still hear it? This is off. Gone? Okay. Weird. I honestly have no idea what that came from. Well, if it comes back, let me know. Thank you. Appreciate it. Okay, where were we? Right. So, outstanding. Okay. So, the key to constructing such a diagram is to recognize the relationship between the four statistical quantities. Right. So we've developed these for individual kind of figures of merit, and we're saying that there's a relationship between them. And the law of cosines. This is just literally the law of cosines. Where A and B and C are the lengths of the sides of a triangle, and theta is the, or phi is, I'm sorry, is the angle opposite C. The geometric relationship between R, E prime, sigma F, and sigma R shown in figure 1. Okay, so essentially we're constructing a geometry in a way that pings off the internal relationships between all of these statistical measurements. And if we do that in the right way and squint at it, we can start compiling things together in a way that's plottable, even though we're looking at more than 2 variables. That's essentially what's going on. Okay. With the above definitions, it is now possible to construct a diagram that statistically quantifies the degree of similarity between 2 fields. One field will be called the reference field, usually representing some observed state. The other field will be referred to as the test field, typically the model simulated field. The aim is to quantify how closely the test field resembles the reference field. Okay. In figure 2, 2 points are plotted on the polar style graph, with the circle representing the reference field and the cross representing the test field. Here's test and here's reference. Okay. Okay. The radial distance from the origin to the points are proportional to the pattern standard deviations, and the azimuthal positions give the correlation coefficient between the 2 fields. The radial lines are labeled by the cosine of the angle made with the absentia, consistent with figure 1. The dashed lines measure the distance from the reference point, and from the reference point, and as a consequence, the relationship shown in figure 1 indicates the root mean squared error once any overall bias has been removed. Okay, so this value is your correlation coefficient. This value is your standard deviation. So my difference in standard deviations. Okay, let's see. Okay. So, the point representing the reference field is plotted along with the absentia. In this example, the reference field has a standard deviation of 5.5 units, which is right there. So that's this, right? That's this distance here. The test field lies further from the origin in this example with a standard deviation of approximately 6.5 units. So that is, oops, this distance here. The correlation coefficient between the test field and the reference field is 0.7. So that is this measurement up here, right, is 0.7. So that's this angle, essentially. Actually, I'm sorry. That is the angle from vertical. So this angle is 0.7. And the centered pattern RMS difference between the two fields is a little less than 5. 4. Okay, so that's the RMS difference is this. Right, so these are delta RMS. Okay. 2 applications. Construction of an unfamiliar diagram is hardly warranted if, as in the example above, only a single pattern is compared to another. In that case, one could simply report the values of sigma f, sigma r, and e prime, and a graph would be quite unnecessary. If, however, one wanted to compare several pairs of patterns, as in the following examples, then a diagram can convey the information with much more clarity than a table. Okay, model data comparisons. Plate 1. This is plate 1. Climatological annual cycle of precipitation over India. With annual mean removed, as observed. Okay. And so these are, so the observed value of rain is this black line, and all these other ones are different models that are attempting to guess what that's going to be. Okay. Rainfall over India is simulated by 20 atmospheric general circulation models, along with observational estimate. The data is plotted after removing the annual mean precipitation, and both the model and observational values represent the climatological monthly means computed for several years of data. The observational estimate shown is from that 94. Okay, the model results are from this shenanigans. Okay, sure. Plate 1 shows that the models generally simulate the stronger precipitation during the monsoon season, but with a wide range of estimates of the amplitude of the seasonal cycle. The precise phasing of the maximum precipitation also varies from one model to the next. It's quite difficult, however, to obtain information about a particular model from plate 1. Yeah, right? Look at all of these models that are being plotted, right? That's a little bit of a mess. So trying to estimate which one of these is better at guessing what's going on, I don't know. Okay. Okay. There are simply too many curves plotted to distinguish one from another. It's important, therefore, to summarize simulated pattern. Okay. This is done in figure 3, where all letters identified computation model results. Figure 3 clearly indicates which models exaggerate the amplitude of the annual cycle, for example, K, Q, and C, and which one grossly underestimate it, I, V, and P. So we go down here. Now we can look. Here's our observational, right? And now we can see that I, V, and P underestimate. K, Q, and C overestimate, right? I believe that's what he said. K, Q, C, yep. It also shows which models' simulated annual cycles are correctly phased, i.e., well correlated with the observed and which are not. So in other words, which ones correctly guess when the model is going to rise and come back down. And that's probably Z, I'd imagine, and A and N. Let's see. Yep. So ZO, A, or AO, Z, and N do a good job of. Where's O? Oh, that's O. Okay. A, O, Z, and N all do a good job of correlating, so they increase when the data increases and decrease when the data decreases, but it doesn't say anything about how much they increase and decrease, right? So this, like, one down here might be matching pretty well with the timing, but the amplitude might be all off, right? Okay. Because they lie relatively close to the reference point. Among the poorer performers, it's easy to distinguish between errors due to poor simulation of amplitude and the annual cycle due to incorrect phasing, as described next. An assessment of whether apparent differences suggested in plate 1 and plate 3 between the models and observations. Okay. So we're gonna then talk about how you decide which one is most significant. Okay. According to figure 3, the RMS error on the annual cycle of the rainfall over India is the smallest for model A. Figure 4 confirms the close correspondence between model A and the observed field. Other inferences drawn from figure 3 can be confirmed by figure 4. For example, models A, B, and C are well correlated with observation, i.e. the phasing of the annual cycle is correct, but the amplitude of the seasonal cycle is much too small in model B, far too large in model C. Model D, on the other hand, simulates the amplitude reasonably well, but the monsoons come too early in the year. So that's what it's talking about here, right? So let's. Here you go. Here's figure 4, right? So, model B does a decent job of modeling the timing, but the amplitude's off. Same with model C, right? Does a reasonable job with the timing, but the amplitude's off. Model D over here. Model D does a good job with the amplitudes, about fairly spot on with the amplitude, but the timing is off, etc. Okay. Tracking changes in model performance. And another application of these diagrams, we can summarize changes in the performance of an individual model. Consider, for example, climatological model, which changes in parameterization schemes have been made. In general, the revisions will affect all fields simulated by the model, and improvements in one aspect of the simulation will be offset by deterioration in some other respect. Thus, it could be useful to summarize in a single diagram how well the model simulates a variety of fields, among them, for example, temperatures, precipitation, and cloud distribution. So that's what this is talking about, right? If I started here and then I moved down here, that's telling me how, in what ways it's improving or not improving, right? I can look at how these things evolve, like I said, into a line over time. Because the units of measure are different for different fields, their statistics must be non-dimensionalized before appearing on the same graph. One way to do this is to normalize for each of the variables the RMS difference in the two standard deviations by the standard deviation of the corresponding observed field. So E prime is E prime over sigma R, or E prime hat, I should say. Sigma F hat is sigma F over sigma R, and sigma R hat equals 1. This leaves the right? So you're dividing out by sigma R, right? You're just dividing everything by sigma R, and so you're normalizing that way. Hey, Toast. Sorry if I'm speedrunning this a little bit. Okay, this leaves the correlation coefficient unchanged and yields a normalized diagram like that shown in figure 5. Note that the standard deviation of the reference, i.e. observed field, is normalized by itself and will therefore always be plotted at a unit distance from the origin along the absentia. So, this point is always the same. We are trying to compare different things to this point, right? And so because of that, this is 1 unit along in this direction. Everything's divided by that. Everything's normalized to that. So that allows you to be consistent across different things that you're looking at. Yes. Please let me know if I'm going too fast. I am, like I said, I am kind of speedrunning this a little bit. Excuse me. Because it's somewhat of a long paper, but this is a very important paper for me. Because a large part of what I'm doing is comparing models. Not this many models, but I'm comparing models, right? And yeah, so There's the skill metric. This is wonderful. Isoline suggesting a measure of skill as defined by 4 on diagram indicates patterns. Go for climatological. Oh, very cool, very cool, very cool. Yeah, right. So I mean, honestly, I wish I had learned this earlier. I just randomly stumbled on these plots, but these plots are fantastically useful for a lot of stuff. Holy cow. But yeah, so the reason why I was sort of speedrunning this is I was trying to get through this, and I know I'm not going to. But so if I'm going too fast, if something is confusing you, if you want me to go over something again, please let me know. Again, this is because this is sort of a research stream, right? The point of this is to force me to go through things that are important for a research mode. So that is one of the primary goals of the research stream is to go a little faster and to do things that are a little more advanced. However, that does not mean that I will not stop and try and explain from the ground up if anyone has a specific question. I will always try and do that. So, yes. Actually, you know what? That's a good point. I'm going to put that on a pinned message. Okay, sounds good. Good to know that you're able to pick that up. What I'm going to do is to stop. Way to slow down. I'm speed running, but always will stop for questions. Okay. So what I'm gonna do is like this, and I'm gonna pin that. There we go. Yeah. Okay, there we go. Now, excellent. And man, this is still running. I'm downloading NASA data, and it's taken forever. Where are we at on this? 2007. Oh, we're getting there. We're end of 2007. It's getting there. Anyway. Yes, pizza. That's amazing. Does it have pineapple on it? I know that's your favorite. Yes. So what I was just saying is I'm sort of speedrunning this really quickly. But if you in an effort to get through the general concepts, but if you have a specific question, if there's something that you're interested in, let me know. Nice. Ooh, Barry. That is a fancy pizza. All right, so maybe I'm wrong about this. Sorry, I just got diverted. Isn't Detroit style the really thick crust, like bready style crust? Am I wrong about that? Because my understanding is Chicago style is a flaky crust that's got a lot of filling in the middle. It's like a pie almost. And Detroit style is just like it's like a bread, a large, almost like a focaccia pizza, I guess is the best approximation. That is my understanding. That's right. Okay. Those are good. I make fun, but those are very good. I do love focaccia pizzas. Um, I how am I doing? Ah, I'm doing. I'm doing. I I was talking with B and absolutely 100% like we were having a conversation. She's like, "Aren't you supposed to be streaming now?" So I'd run upstairs, try and get everything set up, and then I can't find the bloody Taylor plot because I couldn't remember the name of the plot. So I can't find the Taylor plot, and I'm trying to find the silly thing so I can find this paper because I didn't have the paper. It was a mess. It took 20 minutes to get going. So we're doing great, you know. Otherwise, chugging along. Yeah, it was definitely one of those moments where you're like, oh, smooth move, streamer. Anyway, so let's keep rolling. Yeah. So she is feeling a lot better. Glad she got checked out, but turned out not to be anything too serious, luckily. But it was kind of a let's make sure that she's doing okay and checked out, and so everything turned out much better. She's feeling much better. Yeah, that was one of those safe and sorry kind of things, you know. So we're doing okay. Poor Potato is stuck in his cone for another week, unfortunately, because he managed to muck with his incision a little bit, so now he's stuck in the cone for another week, but he'll be good. He'll be okay. So that's how's manager doing, by the way? Hope you guys are doing well over there. Thanks for asking, by the way, Toast. I appreciate you. Oh, that's cool. As long as it doesn't, you know, fall into Fight Club, I think you're good. Ladies and gentlemen, Toast is an awesome streamer. Yeah. Yeah. Toast is an awesome streamer and a wonderful person. Anyway. All right. Focus. I at least want to get through another section of this. So yes. Right. Yeah. She kind of had one of those, really wasn't feeling well, wanted to go get checked out. Got checked out. Things turned out fine. So that kind of thing. But it wasn't like it turned out not to be anything, you know, major, so it was what it was. Sorry, I probably should have told you. Where was I? I was in the middle of doing something. Right, reading. Okay. Back to the math. Okay. Note that the standard deviation of the references, i.e. observed field, is normalized to itself. Right, that's what we said. It's always going to be in that one spot. In figure 5, a comparison between two versions of a model is made. The model has been run through a 10-year, right? We don't care about the specifics of the model. We're interested in the math. They did something to it, right? For each field, 2 points are connected by an arrow that is plotted, the tail of the arrow indicating the original, the head pointing the revised. For each of the fields, the statistics quantify the correspondence between the simulated and observed, right? He's being very explicit about what he's talking about, but we saw that in here, right? You start here, you go here, and you see how it changes, and like, oh, my model improved, or maybe my model went the wrong way. You know, that's how you do these things. Okay. Many of the arrows in Figure 5 point in the general direction of the observed reference point, indicating that the RMS difference between the simulated and observed fields has been reduced. So again, RMS is root mean squared. That's an indication of your error, of your absolute error. For sea level pressure, okay, we don't. Okay, correlation between the two is slightly reduced, right? So if you move this, this direction, your correlation might go down, even though you got to kind of make a judgment. What's the most important thing? Is it more important that your difference in magnitude is close, or is it more important that your alignment of timing is close, right? This is the that's the art of selecting the models and how you build the models, because you're always making trade-offs, right? Very rarely are you going to do something to a model and have it improve everything. Usually 90% of the time you're making a change to a model, it improves A and makes B worse. And again, this goes back to that phrase that I love using and I use all the time. All models are wrong. Some models are useful. And models are useful for different things, right? So I might make a model where that's really trying to get the timing of, in this case, rainfall correct, right? I don't necessarily care that I'm guessing how much rain is there, right? Maybe the amplitude doesn't matter, but I really care about the timing. Maybe that's what's important for me. So what's the use case of my model? That's going to determine what the importance of a specific model is. And sometimes I'll have a whole clump of different models like this, right? And I'll care about them. And you know what? Maybe the offset that I'm saying is, right, I have all these models, and it sure looks to me like, these two are the closest. Those are clearly the best. Those are the ones I always want to use. Well, maybe it takes me, maybe I have to get to a supercomputer and run it for a week to get those models. And I need a daily run of the model. And maybe M, this model over here, I can run in 4 hours. And that gets me close enough, right? If I need to make a daily estimate of what's going on, maybe M is close enough. And the trade-off is it's not going to be as accurate, but I can do it in a reasonable amount of time, right? So that's another aspect of what you're using when you're making the judgment of which model to use. Okay. I think we're just going to jump to 4 over here. Okay, indicating statistical significance, observational uncertainty, and fundamental limits of the expected agreement. Okay. So again, how do you evaluate the results that you've plotted? In the examples we've shown in section 3, all statistics have been plotted as points, as if their positions were precise indicators of the true climate statistics. In practice, the statistics are based on finite samples, and therefore they represent only estimates of their true values, right? Again, you're always approximating. You never have all the data. You always are guessing. Since the estimates are, in fact, subject to sampling variability, then the differences in model performance suggested by a figure might be statistically insignificant. There might be something else going on here, right? So I always go back to the frequency time interchange thing, because for me it's a very well-known thing. I am doing sampling of a signal in time to try and figure out what the frequencies are, right? My sampling rate, I have to have at least 2 samples of my at my highest frequency rate in order to capture that frequency. If my samples are here and here, I'm going to miss this high frequency noise that's going on, right? This high frequency that's riding on it. So, that sampling rate Model discussion is like other life interest behavior. Yeah, right? It's you're always making a judgment. You don't you always have, right? You don't have this perfect, right? We're always talking about, oh, well, what's really going on is this plot, but you don't have this perfect plot. You have this point and this point, and you have to guess what this is based on this point and this point. And so there's a limit on the details that you can guess based on what your sampling rate is, right? So that's going to determine whether the difference between Z and O might be less than the error, the uncertainty that comes from your sampling rate. So you can't actually tell if Z and O, which one is better, Z or O. You don't know. It's in the error, right? You're not sure. That's the point of having error bounds on your data, right? You can't necessarily tell enough of a difference to say that Z is better than O, or O is better than Z, I should say, right? Okay. Similarly, a model that exhibits some apparent improvement in skill may, in fact, prove to be statistically indistinguishable from its predecessor. For proper assessment of model performance, the statistical significance of apparent differences should be evaluated, right? You have to know what your range limits are. Another shortcoming of the diagrams, as presented in section 3, is that neither the uncertainty in the observations nor the internal variability, which limits the agreement between simulation and observed fields, has been indicated. I have no error bars anywhere here. I just have nice, simple points. All right. Even if a perfect climate model were to be devised, i.e. a model realistic in all respects, it would still not agree exactly with observations that are to some extent uncertain and inaccurate. So even if I was perfectly modeling reality, my measurements of the reality are not perfect, right? So I could be off there. So there's always error and uncertainty. In my model, there's error and uncertainty in my measurements, all these things. Moreover, because a certain fraction of the year-to-year differences in climate are not deterministically forced, but arise from internal instabilities in a system, for example, weather noise, quasi-biannual oscillations, El Nino Southern Oscillation, etc., the climate simulated by a model, no matter how skillful, can never be expected to agree precisely with observations, no matter how accurate, right? So there's always more detail going on. And on top of it, weather is a chaotic system. So you are going to have an error doubling rate in your weather that's going to stack on top of this, right? So your uncertainty rate is always increasing between your measurements. And the rate at which it increases is going to be, right? So in other words, it's not your error is not static. Your error increases over time as well. In the verification of weather forecasts, this latter constraint on the agreement is assessed primarily with theoretically understood limits of predictability. Right? Again, that's what I was talking about, right? It's a chaotic system. Even in theory, I know I won't be able to be more than X precise. Right? And I can nail down, the really interesting thing about this, right, is we're talking about this unpredictability. I can nail down with some pretty exacting precision what the limits of my predictability are. That's something that I think is even more fascinating. And I think this ties into a conversation that can be had about quantum mechanics, right? And what does precision mean? I can be extremely precise about how imprecise I am. That's a thing, right? I can mathematically describe exactly what my boundaries of knowledge are. And I might be able to do that with an exactitude that's stronger than the knowledge itself. And again, that's a lot of the description that we see within quantum mechanics is very, very precise description of of the uncertainty, right? I know exactly how much I don't know. If that makes sense. And so that's why chaos theory is a very interesting area of mathematics, because it's doing exactly that, right? It's giving you a formal mathematical way of describing precisely how uncertain I am about something. About things that even in theory we could not predict. But I can talk about exactly how much we can't predict them. So anyway. Similarly, in atmospheric models forced by observed sea temperatures and okay, blah, blah. Okay. Statistical significance of differences. One way to assess whether or not the apparent difference in a model performances shown in Figure 3 are in fact significant is to consider an ensemble of simulations observed from one or more models. For AMIP-like experiments, such an ensemble is typically created by starting the simulations from a different initial condition, but forcing them with the same time varying sea surface temperatures and ice covers. So again, since it's a chaotic system, it's extremely sensitive to initial conditions, right? So a very small initial condition change will compound over time, will end up with a very different outcome, even though the processes are identical. Thus, the weather, and to a much lesser extent climate statistics, will differ between the pair of realizations. In the case of rainfall over India, results were observed from a 6-member ensemble of simulations by Model M. So I took Model M, I slightly varied the initial starting point, and I ran it 6 times. The statistics comparing each independent ensemble member to the observed are plotted as individual symbols below M on Figure 6. So that's Figure 6 over here. I'm going to scroll this in for a second. Here is Model M, and these are all the runs of Model M. They're all grouped together. That is kind of a really bad plot. Anyway, it's very difficult to get across what you're talking about. The statistics comparing each independent ensemble member to the observed are plotted as individual symbols below M. The close grouping of the pluses in the diagram indicates that the uncertainty in the point location attributable to the sample variability is not very large. So in other words, M is not varying very much between runs. A formal test for statistical significance could be performed based on the spread of points in Figure 6, but for a qualitative assessment, this is unnecessary. If Model M is typical, then the relatively large differences between climate models seen in Plate 1 are likely to indicate true differences in most cases. In other words, my run-to-run variation within M is much smaller than the difference between M and O, right? Therefore, I can say honestly that the difference between M and O is pretty large, right? There's a large actual difference between these two models because the internal variation in M is not very big. Assuming the internal variation O also is not very big. The differences are unlikely to be explained by simply differences in climate samples generated by simulations of this kind. A similar approach for informationally assessing statistical significance could be followed to determine whether the model improvements shown in Figure 5 are statistically significant, right? So you're looking at the difference in difference, right? So if I change my model and I look at the difference between, all the variations in my initial model, and then I do the changes and look at all the variations in the model after I do the change to the model, are those comparatively big compared to the difference between before and after? That's all it's saying, right? You're just looking at whether the internal variations are large compared to the external variation. One limitation of this approach to assessing statistical significance is that it accounts only for the sampling variability in the model output, not the observations, right? So there's also variability in the observations. Although an estimate of the impact of sampling variability and observations will not be carried out here, there are several possible ways one might proceed. One could split the record into 2 or more time periods and then analyze each period independently. The differences in statistics between the subsamples could then be attributed to real difference correspondence between the simulated and observed fields and a difference due to sampling variability. With this approach, an upper limit on the sampling variability could be established. Another approach would be to use an ensemble of simulations by a single model as an artificial replacement for observations. A second ensemble of simulations by a different model could then be compared to the single member of the first ensemble, generating a plot similar to Figure 6. Right. So what I could do is I could compare 2 different models, varying one model a bunch to have that be my changes in observation, and the other model over here. Right. Okay. Observational uncertainty. Because of the host of problems in accurately measuring regional precipitation, observational estimates are thought to be highly uncertain. When 2 independent observational estimates can be obtained that are thought to be more or less comparable of comparable reliability, the difference between the 2 can be used as an indication of observational uncertainty. Oof. Actually, you know what? We've been going for an hour and a half. And my throat is starting to get sore. If it's okay with you guys, I think I am going to stop this here. I had wanted to get through, but this is long. This is a long paper. Even as I was trying to speed run it, it's still a long paper. But that being said, I think I got a lot out of this, and I hope you got some interesting ideas out of this as well for anything that you might be doing or any interest you might have in, or even just kind of vague passing interest in how do you compare different models. This is a really interesting way to do it, right? And because it's model agnostic, right, you can apply this to a whole bunch of different things. It doesn't have to be climatological model of precipitation over India. That's the point, right? That's the nice aspect of this type of math, is that you can apply this to a lot of different things. So I am actually going to be applying this probably tomorrow when I start my work tomorrow after the morning stream, the morning collab stream, where Toasty will be a part of as we're playing game. Zephyr, if you're interested, Toasty, myself, Gothic, and potentially Runyar will be playing a game as a collab tomorrow, so the VOD will be up. You can go and watch that on Sunday if you'd like. This is kind of a stream heavy weekend for me. I will be streaming Sunday. I will be streaming Saturday, so it's gonna be kind of wild. At any rate, I do want to change this stream time. I don't like that it's so late on Friday. I have to pick another time to make things work for everyone. I'm trying to make. I want to have a stream that's available earlier in the day. I want to have a stream that's available for the people who are in other regions, et cetera, et cetera, et cetera. So maybe a Friday morning stream. Maybe, I don't know. I'm not sure. I still need Friday morning's not going to work. I'm not sure what the right timing is. Maybe we go back to Thursday morning. I don't know. At any rate, we will be streaming the next couple of days. If I get horrifically bored again tonight, I'm going to try doing some reading tonight, but if I get horrifically bored again tonight, I might hop back on some game. Just for fun. At any rate, thank you all for joining me on this incoherent scream through this paper. Oh, Okay. Yeah. We will be back to continuing the paper that we started last Sunday morning paper. There's the anime watch. When's the anime watch on? I forget. I need to figure out the timing of all this. And then I have to give B enough free time from the dog. Oh, geez. Go set that off, man. And I hear the dog whining. So, yes. How dare you? B had to go to the bathroom. Left dog downstairs. Wrecked coherent. You're not wrecked weird. Yeah. Jeez. Sorry, brain is not functioning right now. Okay. I'm gonna go. You guys all have a wonderful evening. Have a wonderful Shabbos for those doing Shabbos. And I will be back here at the very least tomorrow morning for our giant stream. Otherwise, I will see you all in other places. Mwah. Thank you, thank you, thank you, thank you. Until next time. Goodbye. Thanks, Toasty. You're awesome.